Before I start the course, I want to show you something in the news. If you follow the news, you noticed that a few days ago, a bank called the Silicon Valley Bank broke. Okay, and another bank has also gone broke. And this is threatening a full-blown financial meltdown. How can one bank going broke threaten a full-blown financial meltdown? It's not even the biggest bank. Let me show you again what we saw in the first course. This Silicon Valley Bank is in the middle somewhere. It's part of a strongly connected component connecting all the banks. So if the Silicon Valley Bank goes bankrupt, the banks that it owes money to will not get that money. Maybe they also go bankrupt. And this threatens the whole stability of this whole structure. So it's not just theory, okay? This is a big thing. For one little bank, you see it's actually very badly structured. The race to confront the threat of a full-blown financial meltdown. The world saw one failing bank. President Biden's aides saw a great unraveling. Many other banks have problems. You see, so it's actually very important. So you know why, huh? All the banks are totally connected. And that's an enormous weakness. So what do? They try to bail out the bank. The government is pouring money into this bank so it doesn't go bankrupt, so that the whole structure will not collapse. Okay? Something kind of wrong in this kind of structure, I think. Yes. Yes. But somehow there's no laws, regulations for this. A bank can lend money to any other bank, and this makes all these cycles. And now again we get financial meltdown. Okay. It's just a small thing that I wanted to show you. Another announcement is that next week we will have the midterm, and we'll make a mail on this. During the first hour of the course, the material of the midterm will be the first 5 lectures, and it will be 1 hour. And of course, if you do well, you will already have 5 points on your final grade, up to 5 points. Okay, so I will send a mail on that. So normally it's next week, week 7. If this is a real issue, if it's really hard, the student representative can talk to me. But if there's no real issue, I will hold it next week on during the first hour of the course. Okay. Okay. I think that's it for the announcements. Oh, another small announcement. In a few weeks, you will get the project course. The course project description. And this project will be very different from previous year projects. In fact, you will all be working on finding out how Facebook manipulates public opinion. So we will kind of do a coordinated project, and you will each get a specific task in there, and you will find out in a couple of weeks. And this is also part of the master's project, so the poll I just showed you before is also part of that. It's kind of a preliminary thing. So it's a very different project. So you will be kind of a team in some sense, working on detecting whether or not Facebook manipulates. And each group will collect some data and do some analysis and make a small report on that. And this will be also used by a master's student who will be combining all this information. Okay? No. Maybe you will know who it is. Maybe you don't know who it is. You will find out. Okay, so let me start today. Today we're going to talk about markets. So again, we're going to do game theory. We're in a few 4 more weeks, we're going to do more game theory. But let me first, just to get you really situated, explain what we saw so far and how we're going to organize the rest of the course. Graph theory and game theory are two big pillars. We started by introducing graph theory in lectures 1 and 2, social networks with humans, strong, weak links, positive, negative links, and we saw closure, 3 different kinds actually, for social affiliation, and balance, strong, weak balance, how the networks organize. And then lectures 3 and 4, we saw game theory, where you have players choosing strategies. They have payoffs. We saw pure mixed strategies, dominant strategies, Nash equilibria, which is kind of a selfish, individual rationality. We also saw social rationality, Pareto optimality, social optimality, a little bit about dynamic games. So we saw that. And the rest of the course is basically applying this in 2 parts. We are now going to have a few lectures on applying game, mostly game theory, and then we'll have some lectures on more graph theory. So this is lectures 5 to 8. Last week we saw traffic networks and auctions. Remember the second price? And so the drivers are players, and in the auctions the bidders are the players. And we saw how important the second price auction is. And today we're going to talk about markets. Markets is where you have not just bidding for one item. You have many buyers also, but also many sellers. And the buyers and the sellers interact. And the prices that they're willing to pay is the strategies. And there's each item will have a price that's somehow determined. And that is very important. So that's what we're going to talk about today. And next week, and the week after, maybe because of in midterm, we're going to add something. Traders, like supermarkets or internet stores. And the traders are sitting in between the buyers and the sellers. So you have even more strategies. What are the strategies? And here you can get monopolies, competition. And finally, the final one will be when we have a one node with the neighbors, they do negotiation. In the previous one, each player does one move, okay, and that's it. But negotiation is when they're doing multiple moves. One guy says, I do this, the other guy says, no, this, and then they react. And somehow, the negotiation arrives at some kind of a stable thing, multiple moves. So this time we're going to talk about negotiation. So it's a game where you have many moves. And so again, all of this will be talked about in game theory terms. Okay? And the rest of the course after that will be mostly graph theory. This is 9 to 13. Information networks, search algorithms, the web, how you share information on networks. And we'll talk about different kinds of search, and we'll go in depth into the page rank and variations, which is why Google is so rich, because they were the first to do this. And then we'll talk about cascades. Cascades is when people are influencing other people. I do something, somebody else hears it and follows what I do. And you have different kinds of cascades. You have herding, where everyone is kind of following the leader, and they're all doing the same thing. They're all jumping off the cliff. And then you have direct benefit, when the more people do something, the better it is. So more people buying Word means they can exchange documents. So that's a benefit. But if only one person in the world is using Word, they can still make documents, but they cannot share. So the more people you do it, the more you have benefit. And final one is cascading on the network. So if I hear somebody close to me doing something, and maybe I follow them or not. Okay, so different ways people influence other people. And the final thing we'll see is large-scale properties, power laws, something called the long tail. Why Amazon has millions of products. Why supermarkets have huge number, 10,000 different products. There's a good reason. And we'll also go back and talk about small world phenomena. Okay, so that's how the whole course is organized. So you see how it works. Then the first 4 lecture kind of intro. Then we have 4 lectures which is mostly game theory, so you really get some good intuition on game theory. And then the final part will be mostly graph theory applications. Okay? So today we're still doing game theory, and now we're going to markets. A market is, it's like an auction, except you have many sellers, not just one seller. I remember last week we saw auctions. Just easy to pronounce. Okay, so last week we saw auctions, many bidders, so buyers, and one item. So they're like competing for this one item. But market is like N. Auction is N and 1. N buyers and 1 seller. Market is N buyers and N sellers. That's what we're going to look at today. So you have many participants. And so a market is very general. It's whenever people come together to exchange stuff. Some people will give the stuff, some people will get the stuff. Sometimes you use money, or you can use barter. Barter is where you trade things. So money was invented as a way of avoiding having to always trade. You can buy something for money, and you can use the money later for doing something else. And so then all the things you buy have a price. Okay? So the price is a coordination mechanism. So this is something maybe people don't think about. What are a price? A price is a way of coordinating the buyers and the sellers. Okay, so picking the right price is important, and it's applying game theory. And so there's many kinds of markets, of course. Consumer markets, internet markets for lots of stuff, financial markets for different kinds of financial assets, stocks and bonds and money that can be traded quickly. So that's markets. So we're going to study that. So last week we studied auction, and we showed how important the second price auction is. It's really the thing. You bid your true value. And today we're going to study markets. Okay? So markets are complicated. So we're going to, as usual, make an idealized market and study it. And this one gives us intuition that we can apply all over. In the real world, you can make these concepts more realistic, but the intuition is still true. Okay? That's usual. This is the main principle in the course. Today, we're going to talk about markets and what's called matching. Matching is when all the sellers can sell and all the buyers can buy. Everybody's happy. Okay? All the sellers sell their stuff and all the buyers buy something. And the way to do that is to choose the prices. People talk about supply equal demand, but that's kind of a phrase, but we're going to see what it means. Okay? And then the next 2 weeks, we're going to add intermediaries. These are like stores, supermarkets or Amazon. So they're not actually buying and selling. They're just taking from the seller and giving to the buyer. They're intermediate. And finally, we're going to talk about negotiation. Okay, bargaining power, how you negotiate. So, but today we're going to talk about supply equal demand. Okay? So, the general approach, we're going to make an idealized model, a simple formal model, and we're going to prove some theorems today also, some properties, and these intuitions then apply. So, just to summarize a little bit, we did already many cases of this, social affiliation networks. The focal points, the foci, are form a model of why people are making frictions, okay? And then structure of balance, the formal model of friends versus enemies. Games, form a model of competition, cooperation. Pareto, social optimality, formal model of how do you benefit society, okay? And today, matching markets, how prices are the key. Prices, how it works. How does a price, the price is coordinating supply and demand. Okay, so let me start. I start with a simple example, and then we make like a real bigger example. So the simple example is called a bipartite matching market. A matching market is where each buyer has one seller, and they match. It's not like many, and many. You have 1-to-1, okay? So it's this kind of simplification, but it's very important because it's actually kind of an ideal case, and in the real world, you want every buyer to have an item, and you also want every seller to sell. So this is good idealization. And when you have perfect matching, it means everybody's happy. It's a bijection between buyers and the items and the sellers. So they're the goal, since they make everybody happy. So we're going to talk about how to get perfect matchings. And the way to get perfect matchings is prices, choosing the price. And somehow the price is chosen kind of automatically. Nobody is actually deliberately fixing the price. So the price is somehow converging. So we'll talk about that. Okay? So decentralized coordination. There's no one person deciding what the price will be. It's decentralized. Everybody is doing something. And also, the buyers and the sellers, they're not the same. They might have different preferences. Also, you want optimal social. You want to benefit society. It turns out that perfect matches are socially optimal, which is very good. So each buyer is selfish, okay? They want to buy the cheapest, and each seller wants to sell for the most, and whatever. So they're all selfish. But in this kind of a market, when you have perfect matching, it's actually socially optimal. That's very good, huh? So this kind of capitalistic mechanism is actually giving you the best benefit for society, and we'll prove that. So this mechanism is actually a very good mechanism, the market, the concept of a market, okay? Of course, humans have been doing that for many centuries, markets, huh? And the reason why they keep doing it is because it works, okay? So we're going to see that. So price is really the concept, okay? So let me give you a simple example. So we're going to start with like real concrete example. Here is what's called a bipartite preference market. So it's bipartite because you have the buyers here and the items there. So here, in this example, the items are not really sellers, they're rooms, okay? This is a dormitory, and these are students. Vikram, Wendy, Shin, Yoram, and Zoe. You can see the names are well chosen. And each person has preferences for certain rooms, okay? Okay, so this is called a preference market. So Vikram would like rooms 1, 2, and 3. Why? For some reason. Maybe because the rooms have a beautiful view, or maybe because they're at the end of the corridor and he doesn't want noise, or whatever. Okay. Whereas Wendy is only interested in room 1, and Shin is only interested in room 2, and so on. Huh? Yoram is interested in rooms 2, 3, 4, and 5. And each room can only have one student. So this has 5 students and 5 rooms. Okay? And the trick is, how do you match students to rooms? And this and bipartite graph, okay? Note here in parentheses, this is a matching market, but they're not always bipartite. So here's an example where it's not bipartite. There was a swapping business called SwapTree. This was in the olden days when there was something called DVDs. Maybe you've heard of those things. You can still find them in museums and so on. Maybe you still have some as relics in your house. So each customer gives a list of DVDs they want, and the list they want to trade, and then they send it to SwapTree, and then they can trade DVDs. In this market, the buyers and the sellers are the same. Okay, each person is both buyer and seller, so it's not bipartite. So this is we're not going to look at this, but the bipartite is more kind of a general thing that will be more useful when we look at examples. We'll generalize it. So here's an example of a perfect matching. Okay, so Vikram goes in room 3, Wendy in room 1, Shin in room 2, Yoram in room 4, and Zoe in room 5. And every student is happy. This is called a perfect matching. This is what you want. Okay? Everybody's happy. All the rooms are occupied and everybody has a good room. Okay? So this is a technical concept in a graph. It's an assignment such that each node has an edge. So there's one edge connect on each node. And no two left nodes are assigned to the same right node. So there's no conflict. Okay? That's a perfect matching. Okay, but not always graphs have perfect matchings. The world is not perfect. And so I'll show you a case when it's not perfect. So here's a little bit different, slightly different example. I just slightly changed the graph. You can see if you compare. Now there's no perfect matching in this one. There's no way to make everybody happy. That's not nice, okay? And we can prove it easily. And the way to prove it is to talk about something called a constricted set. If you look at Vikram, Wendy, and Shin, all those three of them, if you look at all their preferences, NS, it's only 2 rooms. Okay? So here you have a set of people on the right, of buyers, and if you map it to what their preference is, you only will have 2, which is less. So the size of NS, so NS is the neighbor set, it's the set of rooms. NS, the size is strictly less than the size of S. So that's clearly a proof that you cannot make it perfect. Okay? It's not perfect. Too bad. Okay, not perfect. So this is an interesting concept, a constricted set. And it's like a proof, it's a witness that there's no perfect matching. So of course we want to fix that. Later on we show how using prices is actually going to make it perfect when it's not perfect. But here there's no prices. So there's a theorem. If a bipartite graph with equal numbers of right and left node, right nodes has no perfect matching, it must contain a constricted set. So if the graph is there's no perfect matching, there is something like this in it. There is some thing where some of the people only have less things that they prefer, okay? There exists a constricted set. So I'm not going to prove this because the proof is too complicated. It's actually in the book, but it would be too long. The way to prove it is to start with a maximum matching, as many nodes as possible, and try to add one extra node. And of course you cannot, because the matching is maximum. And by doing that, you can actually construct a constricted set. But I'm not going to show that. So the idea is to try to make it perfect, and you'll see that it doesn't work. Okay, so no perfect matching, there must be constricted set. Okay, so that's not good, right? Some people are unhappy. So we want to make everybody happy, and we add prices. So with prices, we'll be able to make everybody happy. So let's extend it now with prices. So here, it's not really money now, because we're choosing rooms. So we're calling it valuations, which is like how much they think it's worth to them. Okay, so here, for each person, so here we have a simple one with 3, Shin, Yoram, and Zoe. So Shin has 3 valuations, 12, 2, and 4. That means Shin really likes room 1, gives it a value of 12, doesn't like room 2 so much, only value of 2, and likes room 3 a little bit more, so 4. So the 3 numbers give the value of each of the rooms for the person. Like 8, 7, 6, Yoram would like room 1 with 8 value, and room 2 with 7, room 3 with 6. Okay? Okay? Now, when everybody chooses a room, they will have, each person will have a value. Like if Shin chooses 3, that'll be 4. If Yoram chooses 1, it'll be 8. Zoe chooses 2, that'll be 5. So you have 4 plus 8 plus 5. The sum of all that is called the quality of an assignment. Each choice of rooms gives you some quality, where you add the valuations. And the optimal assignment is the one of highest quality. That's reasonable. If you can't make it perfect, you try to make it as good as you can. So for example, we give Shin room 1, Yoram gets room 3, and Zoe gets room 2. That makes 12 plus 6 plus 5. That makes 23, okay? That's actually an optimal one. You can't do higher. So you can prove that as exercise. Question?
Ça dépend de à quel niveau on met l'optimum. Par exemple, si y a quelqu'un qui avait une évaluation à 0, mais que les autres ont une grande satisfaction, là on aurait un maximum optimal par rapport à ça. Mais quelqu'un qui a 0, c'est pas.
Oui, c'est ça. So the idea is that it's not because it's globally optimal that everybody is going to be happy.
Oui, voilà.
It may be in the global optimal, somebody will be less happy, but you can't do better, is the point. You can't. So here we're kind of making advantage on social benefit, okay? The optimal one is the one that makes the total amount of happiness is the highest. Okay? But we will see later that we're actually going to have both. We will satisfy both, where each person will choose the thing that's best for them selfishly, and it's socially optimal. Not in this example, but in a real market when you have prices. So here there are no prices because the rooms don't cost anything here. They're free. And these valuations are just how much it's worth in the head. So there's no price for the rooms. But when we add price, we can actually make it so it's best for the individual and best optimal. But not in this case. So proving this is optimal is exercise for you. Just try it. And you can actually think a little bit, try other ones, and you'll see that there's no way to get a higher value. And you can prune things. That means at some point you can say, it's not possible. If I keep going, if I start assigning, and you can show that, for example, if I start assigning 2, I know the third one will never make it higher than 23, okay? So if I do 4 plus 8, if I assign the first 2, that's 12. Well, the highest I can add is 7, that's 19, so it's less than 23. So clearly, the 4 and 8 will not be part of an optimal assignment. So you can prove like that. Also, another exercise for you, when you're studying this, the original problem is a special case of this. So the original problem is when you have no prices, but just preferences. Just list of rooms that I would like. So basically, what it means is that I like some rooms equally, and I don't like the others. So it would be like 11100 or something, huh? Okay, so I didn't say anything. Can you prove it? You should prove that. Okay, so this is the case when you add these valuations, but still it's not really prices yet, huh? Now let's add prices, and we'll see that adding prices actually will solve all the problems. It will make everybody happy and make a social uplift. That's kind of interesting, huh? So let me show you how it works. So now I'm going to do another example, a more realistic one. So what you saw just now was like warm up. Now I will do a housing market. This is like a realistic example. You have people who want to buy a house. So you have a collection of sellers who want to sell houses and buyers who want to buy the houses. Okay? Each seller I has a house for sale, and each buyer wants to buy a house. Okay? Each buyer has an idea of how much the house is worth for them, valuation. So this is two indices. Huh? So if there's three houses for buyer J, it would be V1J, V2J, V3J. So buyer J might like the first house a lot, but might not like the second house. But maybe another buyer would love the second house, okay? Because the second house is closer to a school, for example. So they have different valuations, okay? Non-negative integers. And the sellers, up to now, they start with valuation 0. So that means the seller also ranks the buyers, but they're all the same. So the seller doesn't care who buys. Okay? So basically the buyers rank the houses, but the seller doesn't care. So we're assuming the seller is not a racist who only wants to sell to white people or something like that. Huh? The seller will sell to anyone here. Okay? So the seller wants to sell the house and makes a price. PI. This house costs 250,000 euros. Okay? And the buyer buys the house, and the buyer will have a payoff. Okay, so this is like a game, huh? The setting of the price is like a move in the game, a strategy, and the selection of the house by the buyer is a move, is a strategy. Okay, so the buyer gets a payoff. So if the buyer thinks the house is worth 300,000 personally, but it's 250,000. Then the buyer has like a win, a gain of 50,000, okay, in his head. So the buyer, of course, wants to maximize their payoff. They look at all the prices, they look at their valuations, and they will pick the house which has the highest. So it's selfish. Selfish action, okay? Okay? If there's a tie, any can be chosen. So sometimes there's a tie. But if the price is too high, then the buyer will not buy. Okay, if the house costs 500,000 and the buyer only thinks it's worth 250,000, they will not buy, and the payoff is 0. Okay, so they will not tolerate negative payoffs. Okay. Okay, so here is then how it works. Okay, so this is an original example. We have sellers, ABC, buyers, XYZ. Each buyer has 3 valuations. So these are the same as the 3 guys, the 3 people who wanted rooms, okay? But now we have an extended version. So we add another column here, which is the prices. Each seller puts a price on the house. So A's house is worth 500,000, well, that's what the seller wants. B wants to sell it for 200,000. C is giving away the house. That's weird, huh? That sometimes exists. If you noticed, if you read the news, there was actually a village in Italy which was selling houses for €1. Of course, the houses were dumps, okay, and you need to do some investment to make it livable, but you would be the owner for €1. So it's this can still exist, can exist, okay? So now we can see what happens. So look at the buyer X now, okay? We can calculate the payoff. Buyer X values house A at 12, but it costs 5. So the payoff is 7, okay, for house A. And for house B, its value is 2, and the value is 4, and the price is 2, so the payoff is 4 minus 2 is 2, and for 3, it's 2 minus 0, which gives 2. So you see, the first one is still the highest, so X wants to choose A. Fine. But look at Y now. Y has 8 for the first one, but the price is 5. So the payoff is 3. And 7 for the second, the price is 2, so it's 5. And 6 for the third, but the price is 0. So the payoff for the third one is 6. So Y is going to choose C, okay? The highest payoff is selfish. And if you calculate the same for Z, I will leave that up to you. You will see that Z chooses B. Oops. Z chooses B. So we're good here, huh? It's a perfect matching. Somehow, the prices have magically made everybody happy, okay? They have resolved the contention, okay? We say the prices are market clearing. So this is a technical term from economics. It means that after everybody does their stuff, nothing is left. It's cleared. It's empty. Okay? So with these prices, all the sellers sell their houses and all the buyers buy, so there's no houses left and everybody is happy. So the prices are market cleared. Of course, that's lucky. We're lucky here, huh? We're lucky. That's not always the case. You get market clearing. So here's another example. Okay. So we have the same valuations for the buyers, but the prices are different now. 210. Okay. So instead of the previous one, it was 520. Now it's 210. So what does it mean? Well, X still wants A, but look at Y. Y has 876, so 8 minus 2, that means 6 for house A, 7 minus 1, 6 for house B, and 6 minus 0, 6. So 666 is the payoff. So Y would like any of the three, okay? And Z also wants A, if you calculate it, okay, the highest payoff. Oof, the prices are not market clearing in this case, huh? They're not. Wow, doesn't always work. But we can make it work if we change the prices around, okay? So here's another example. Okay, here's an example with ties and tie break. So here the prices are 310. Okay, so X wants A, Y will either want B or C, and Z will want B or A. So you can see there's some conflict, but if you choose rightly, you can resolve. Okay, so if buyers Y and Z agree not both to go for house B, they coordinate, so each gets a different house. Okay, so Y will get C and Z will get B. Then they are market clearing. So here it's market clearing when the buyers coordinate a little bit. They tie break. Okay, so with a little bit of coordination, the prices can again make it market clearing. Okay. Okay, so let's think a little bit about that. So you see how powerful the prices are. If you choose them right, sometimes it seems you can make everybody happy. but otherwise, you don't make everybody happy. So what can we say? We can actually prove properties. So this is a formal model, and this models pretty well a lot of real situations. So let's think about what's going on. So market clearing means the supply is equal to the demand, so there's no leftover. So if you look at economic theory, so far I haven't said so much about the theory. The prices are supposed to adjust up and down to ensure somehow, magically, supply equals demand. So right now we don't know how that works, okay? We don't even know if it's possible, okay? So according to economic theory, if all the buyers and sellers, they know all the information, and there's no friction. People talk about friction. Friction is something that stops you from changing prices, like tax or regulations or something that stops you from changing the price. So assuming there's no friction, and if the sellers can set the prices whatever the way they want, then it seems maybe you can always do market clearing, okay? The preferred seller graph has a perfect matching, okay? And it works, okay? So that's one thing. So if you notice here, all the buyers prefer house A. House A is really an excellent house, huh? Everybody prefers house A. So you think, how can we make people happy? Well, the numbers are different, so they're not willing to pay the price. You want this super excellent house, you have to pay the price, okay? And that is what makes it work, even though everybody prefers A, okay? Okay, so there's actually two properties that we can prove. And we'll show you the proofs, okay? So it's like magic. If you set the prices in the right way, then everybody's happy. And the selfish buyers will automatically claim all different houses, and everybody's happy, even though the buyers are selfish. Okay? But actually it works. And there's two properties that we can show. First of all, we can always get it. So I didn't prove it yet, huh? I didn't actually prove this for you. In a bipartite matching market, there exists a set of market clearing prices for any set of buyer valuations. It's not totally obvious, huh? For any possibility, for any number of houses, valuations, the red ones are the ones that you choose. There exists prices that gives you a perfect matching, okay? That's something you can prove, and we will prove it later on. And there's another nice property. Market clearing prices are socially optimal. That's kind of very interesting, huh? For any set of market clearing prices in a bipartite matching market, a perfect matching has the maximum total payout. That's social optimality for sellers and buyers, for any assignment of sellers to buyers. So the perfect matching is socially optimal according to the definition we saw. It's the maximizing the sum, okay? So, yeah, of course, as was remarked before, it doesn't mean that everybody will be perfectly happy, but still, everybody is choosing their best choice, okay? Selfishly, their best choice. So they're as happy as they can be, in fact, with the prices. So these are important properties. So the first one, prices are always converging. There will be some market clearing prices. And the second one, the selfish choices are socially optimal. So this is nice. This means this market mechanism with prices is actually a very nice mechanism. Yeah?
Mais je me demandais, parce que ici on voit le graphe de manière statique, mais
Oui.
normalement c'est quelque chose qui évolue dans le temps.
Ah, oui. So, yeah, so the question is, this is a static graph. So the number of seller buyers fixed, but in real life, there can be new buyers coming or buyers going away, new sellers. Yeah, that's true.
Et les prix augmentent aussi, parce que si deux personnes veulent la même maison, ben, le vendeur va les départager.
We, so if everybody wants the same house, then we will see the way to make is to increase the price. So the price of that house will increase. Okay? So that's intuitive. Huh? If I'm selling a house and there's a lot of people who want this house, I'm in a good situation, right? I can increase the price. And that's exactly what we'll see. The more people who want, but that's because people value my house. Okay? Here, in this example, everybody values house A very much. But even with the price, they still get positive payoff. Huh? So if X buys A, they still have a payoff of 7. They're still gaining, huh? Only the seller gets a piece of the cake, if you want. Huh? If the seller has a lot of people interested in their house, they can increase the price. And what that means is that the buyer will get less payoff, but still greater than 0. Huh? And the seller will get more payoff, the price. So the more buyers you have who are interested in a house, the more that the seller, the more be a part of the cake, if you want, goes to the seller, and less to the buyer. Okay? So that's all this model, all it shows this. Okay? Okay. Let me now prove these two things. But the first thing I want to prove, the easiest one, is social optimality. Social optimality is actually kind of straightforward. We can show it on one slide. So let me show the social optimality. Okay. It can be proved with a simple argument in this model. So we assume we have a perfect matching. And now let's prove it's socially optimal. So basically, what does it mean? We know that every buyer has made a selfish choice to maximize, okay? And we have to show that this also maximizes the sum. That's what we have to show, and then we know it's socially optimal, okay? Okay, so that's a little bit of reasoning, but maybe let me make a break, and then I'll explain the reasoning after the break, okay? What that equals. Very nice discussion. It turns out a free market, a market that obeys these laws, is actually a very good system because everyone is happy individually, they're maximized selfishly, and it's socially optimal. And the only way that this thing can go bad is if someone cheats and doesn't follow this rules, okay? Or monopolizes, or maybe the sellers, maybe there's not different sellers, maybe it's always the same seller, and he's monopolizing the situation, okay? But if you follow this model, then the situation is good. So in real life, the role of the government then would be to ensure that people don't cheat, that they actually follow the model, okay? But today I want to show you the actual model and why it's good, okay? First, let me go through the proof of social optimality. So we have to prove the following. Each buyer maximizes their payoff. Okay? So they're selfish. Okay? And the idea is that the final, the perfect matching is socially optimal. Is socially optimal. So that's a very nice result, okay? And it's not completely obvious, huh? that the selfish solution is also the socially optimal, so that people can act selfishly and it benefits everybody, the whole society. Okay? So in this model we can prove that. So that's a good reason why that the government should make sure that you cannot cheat on this model. So let's prove it. So the proof is we're going to actually follow this direction. Okay? From this we have to show this. So we will do some computations. So first of all, you can compute the total payoff of sellers and buyers. That's the overall thing. So that has to be maximum, huh? For socially optimal. The total payoff of sellers and buyers, it's the sum of the buyer's payoff plus the sum of the seller's payoff. Okay? The seller's payoff is the prices, what they get for the houses, and the buyer's payoff is their own valuation minus the price, the benefit they get. Now, we actually have a perfect matching, so that means every house will get bought. That means all of the sellers will sell and all of the buyers will buy. So maybe the order is different, but all the plus PIs here will cancel there. You see? All the sellers are here and all the buyers. And so all the minus PIs will have a plus PI because it's a perfect matching. Okay? So the PIs cancel. So the total payoff is just the sum of the valuation of the buyers. It's the sum of what they think the house is worth. Okay? Each house is worth what they have chosen. So that's one thing. But now we want to make this step. Okay? Each buyer, okay? Each buyer maximizes its payoff. Okay? But if you look at this total valuation, so the total payoff of the buyers, we'll make a computation, is the sum of all the buyers' payoffs. Okay? And so it's the sum of the valuations minus the sum of all the prices. Okay? So the sum of all the valuations. So this one is maximized. Okay? The buyers, each buyer will pick the VIJ that's maximum. Okay? So that means this sum, the buyers maximize it. And the second part here is actually a constant. Okay? Once you have a perfect matching, this is the some number, okay? So the total payoff of the buyers is therefore maximized, okay? So the total payoff of the buyers is maximized, but the total payoff of everybody is the total payoff of the buyers plus the sum of all the prices, okay? So the total payoff of sellers and buyers is also maximized. Okay? You see that? So you basically have to make this step. So each buyer will pick the valuation that maximizes, and for given seller prices, the buyers are maximizing given constant seller prices, and the thing that you use to prove this is that it's a perfect matching. That's what makes it work. Because here, sum of all the sellers, it's perfect matching. So every seller is there once. It's perfect matching. So every buyer is there once. And that's what makes it work. Okay? So that's how we show the payoff of the seller and buyers is also maximized if each buyer maximizes its own payoff. Okay? So it's socially optimal. And it works because it's a perfect match. Okay? So that's one thing. That's the social optimality. Now I want to show the other thing, that you can always find prices. You can always find prices. It always works. There's always some prices that make everybody happy. That's not totally obvious either. Okay? So we're going to prove that by construction. we're going to let the prices increase until everybody gets happy, okay? So this is the thing that I'm going to show. So we take an arbitrary set of phi evaluations. I'll show you a procedure, an algorithm, and it's actually kind of an auction, because you know in an auction the price goes up, ascending price auction. Well, here also the seller prices are going to go up, but it's not one item, it's all the seller prices can go up. So it's kind of a generalized auction, okay? So we're going to gradually increase prices, but we're going to show that if you do that, all the conflicts will disappear. And eventually, you will get prices where there's no conflict, and so you have a market here. Okay? So it's an algorithm. So I'm going to show you an algorithm. Oops, there. And then I'm going to show you a proof. So we're going to do some kind of a monotonically decreasing number there, okay? And we'll see that it always works. So here's the algorithm. So all the sellers start 0, and buyers choose their preferred sellers, okay? But if there's a conflict, then it's not good enough. But if there's no conflict, if there's a perfect matching, we're done. Fine, okay? And everything's okay, and everything is perfect. But if there's no perfect matching, then the prices are wrong. So what do? We have to increase some prices. But which ones? Well, remember the concept, the constricted set. There is a few buyers. There is a few buyers who, like 3 buyers, and they all want 2 houses. Or 5 buyers all want 1 house. So there's a constricted set, okay? So we look at the constricted set, S, and the neighbors, but there's 5 buyers and they want 2 houses, for example. So what it means is, and this is an intuition too, the sellers are in high demand. Maybe, and S is only 1 house, house A, and maybe there's 5 buyers who are interested in house A. Okay, constricted set. What is the seller going to do? What would you do? Well, the seller is going to increase the price. Okay, so that's what's going to happen. The seller will gradually increase the price until the buyers fall out, until they fall away. Some buyers say, oh, this price is too high for me, boom. And then there's only 4, and 3, 2, 1, and when there's 1, it's done. Okay? So the sellers in the neighbor set, they're in high demand. And so what do? They increase the price. They increase their price. So this is not cheating, huh? It means that they will get more of the cake. The buyers will still get a benefit, but a little bit less because of the conflict. The conflict, that's the consequence of a conflict, is that the seller gets more of the pie. Huh? So the prices will gradually increase. And each time you find a constricted set, you increase a little bit. And at some point, there will be no more constricted set and you're done. So that's what we have to show. So eventually there will be no more constricted set. Okay? So this is kind of an auction. So here's like the algorithm. Huh? So it goes in rounds where the prices are increasing. So we start with some prices, but the smallest one is always 0. That makes things a little bit simpler. We assume the smallest one is always 0. We construct the graph, the preferred seller graph. Each buyer has its selfish choice, and we see if there's any conflict. If there's no conflict, if there's perfect matching, we're done, and it's over. If there is a conflict, no perfect matching, then we have to find a constricted set. We have to find a set of buyers who are somehow in conflict, and the sellers, this is the neighbor set, NS is the sellers who are in high demand. Okay? Each seller in this set simultaneously raises their price by 1 unit. So the prices go up a little bit. Okay? And then you repeat. But you always, we add this extra step, you always want to kind of normalize it so the smallest price is 0. So you don't have things that go forever in very high, okay? But this doesn't really change anything. It's like a reduction. You subtract the same amount from each price, the smallest price becomes 0, and then you repeat, okay? So it's like an auction where prices are always going up a little bit, but it's not always the same item. Here we have many items, and some subsets will go up. And each time it goes up, some buyers, they give up, they drop out. Okay? So let me show an example of this. So here is an example. So again, we keep the same valuations, 3 buyers and 3 sellers. So we start with 0, 0, 0, 0. So what happens? Well, everybody wants house A, okay? So that's not good. So that's a constricted set. So X, Y, Z is the constricted set. So everybody, and NS is just A, okay? They all want house A. So A is very happy. A increases the price to 1, okay, here, 1. So what happens now? So when you increase the price to 1, the selfish choices will change. So X will still want A. Y now will either want A or B, because Y has a valuation of 7 and 7. So Y will do A or B, and Z will still want A. 6, 5, 2. Okay, so that's the end of the first round. Now we go to the second round. So the prices are 1, 0, 0. But again, we have a conflict. Again, a lot of people want house A. Okay? But we don't need to know all of them. We just need to know some constricted sets. So for example, X and Z both want A. And for that set, the neighbors is A, because they each want only one thing. So both X and Z want A. So who's going to get it? We will see. So the seller says, great, I have 2 buyers, potential buyers, I increase the price. So the seller again increases the price. And what happens now? Now we recalculate again the graph. See, X still wants A. Y now doesn't want A anymore, because A would be 6, but B is 7, higher. So Y only wants B, but Z will take either A or B. That would be 5, 5. 7 minus 2 and 5. So so there's still a conflict. So we go to round 3, and the prices will keep going up. So in round 3, we see that X, Y, and Z, all together, they want A and B. Nobody wants C. So, constricted set. A and B are both very happy. They increase the price. From 2, 0, it becomes 3, 1. Okay? And now, we have a new graph, this one here. We can see now Y has increased its possible choices to B and C. Finally, somebody wants C, okay? For Y, B is now too expensive. Or no, it's equal with C. So finally, somebody wants C. And now we go to the next round. We look at this graph. And hey, whoa, there's a perfect matching. X chooses A, Y chooses C, and Z chooses B. We're good, and it's done. So you see the prices have slowly gone up, and each time buyers drop out when it gets too high, and eventually we end up with a perfect matching. So that's how it works. But now we have to prove it, okay? We have to prove that this auction will eventually end. Oops. That it will eventually end. But it will only end if there's a perfect matching, huh? So we have to show that it will end. That somehow it will be over. How do we show that it will be ending? Well, we can define a number that somehow tells us what are the conflicts in some way. So we define some number that's not negative, like a potential, and it's always decreasing. It's always decreasing, but it's always greater than or equal to 0. So if every time it actually decreases, and it's greater than or equal to 0, that means eventually it will end, okay? So we define it like this. Potential of a buyer is the maximum payoff it can get. Potential of a seller is the current price. Potential energy of the auction, it's like the sum of the payoffs, huh? So the sum of the potential energy of the buyers and sellers. So this is actually the payoff of all the buyers here. And here the price is the payoff of the seller. So the potential energy is like the potential overall payoff. So it starts very high. But that's too high, too many conflicts. Okay? So initially all the sellers are 0. And each buyer will pick the maximum valuation. Initially, so if we look at the example, initially it's all zeros here, so the initial potential will be 12 plus 8 plus 7. Okay, so 12 plus 15, 27 will be the initial potential in this example. Okay, but these payoffs are always non-negative. So this potential energy is always greater than or equal to 0. And we have to show now that each time you make an iteration, it will strictly decrease. So basically, intuitively, it starts with some very high payoff, but too high. So the payoff has to go a little bit lower. It lowers until we have no more conflicts. Okay? So the potential energy, where does it change? So there's 2 places. 5 and 6, let me first show the algorithm again. So there's 2 places where the potential energy can change. Here is where each seller raises the price by 1 unit. That changes potential. And then in 6, where you normalize the lowest price to 0. Okay. So that's the 2 places where the potential is changing. So the first one, do the easy one, the reduction step. If we subtract some number p from each price, so we take the minimum price and we subtract that so that the lowest price becomes 0. Okay, so each seller goes down by p, but each buyer goes up by p, and we're summing all sellers and buyers, so there's no effect. So this has no effect. It's just like normalization. So the real thing is here. All sellers in NS raise the prices by 1. So you have 2 sets actually, S and NS. So NS, every seller in NS goes up by 1. And every buyer in S goes down by 1 because we subtract the price. But the size of S is strictly bigger than NS. So these 2 are not going to cancel. Okay? The potential energy in the auction will decrease by at least 1 because S will be at least 1 bigger than NS. So this proves that the potential energy will go down by at least 1. And it starts at some number which is greater than or equal to 0. It cannot drop to 0, so it must end. Okay? So this works because of the theorem of constricted set. We are relying on this theorem. So you can say, why does this magic thing work? It works because if the matching is not perfect, there exists a constricted set. That's actually a strong property, and we're using that here. Okay? That's the thing that we're using. That's the heavy lifting. Okay? Okay, so we saw now, so this shows that this auction will eventually go to an end. So we have proved this. Two properties. Which one we just showed? We proved that the prices will eventually cause all the conflicts to go away. And secondly, the selfish choices are socially optimal. Okay, that's what we showed. Now let me show one more thing. Okay, so today we talked about markets, end buyer and seller. Last week we talked about auctions, and which seems somehow, so I called this algorithm, I called it an auction, but it's not the same as what we saw last week. Second ascent price auction or ascending bid auction, where all the bids go up and then you buy one item. Here we have n items. But still, we can make a connection. Markets and auctions are actually connected. Okay? So it's nice to have them be connected. It's very similar. So an auction is actually a special case of a market. And we can prove that. So let me show here how it works. So I showed in the algorithm, the bipartite magic market is a kind of complicated auction where end sellers, the prices are sort of going up until there's market clearing. But actually, what we saw last week is a special case of that. How does it relate to the single item auctions we saw before? It's actually a special case. We can actually create a single item auction using the market, as a market. So here's how it works. So assume we have n buyers and one seller. So that's an auction. So here in red, we have 3 buyers, and this is the bids, the true values. Sorry, these are the true values, 1, 3, 2. And we create kind of a fake market here. So we have one, this is the item, A. So there's only one item. But we create fake sellers here, B and C, to have the same number. Okay. We add n-1 fake sellers. And we give valuation of 0 for the fake sellers. So how does the algorithm work for this? The algorithm we just saw actually works exactly like ascending bid auction, second price auction. So here's an example. So here's the initial thing. So from the auction, we created this kind of fake market. And we're going to raise prices now. Okay? So remember, the algorithm looks for constricted set. Well, here we have, it's very simple. We have x, y, z is S, and ns is A. So we have the constricted set is x, y, z, and the neighbor is A. So what's going to happen? Well, A is going to raise the price. That's exactly like an auction. So that's raising the price. So the constricted set is all buyers, and NS is the real seller, which is only one seller. The real seller raises the price, so the price would be 1. But there's still a conflict. And you keep raising the price until the buyers drop out. You can see if the price goes high, then the buyers will disappear. Okay? Here, for example, if the price is 2, buyer 1 will not go for A. So that the B and C is kind of not important here. Right? If the price is 2 here, buyer 1 falls out. Buyer 3 stays in because the benefit is 3, and buyer buyer 2 stays in, buyer 3 stays in, but just barely, yeah? 2 minus 2 is like a tie here, 2 and 2. But if you increase the price even more, then this one will drop out, okay? Finally, if you keep raising this price of A, only one buyer is left. The others drop out. That's exactly like a second price auction. So at the point where one buyer is left, it's exactly when the second guy drops out. It's like in an auction, huh? So the price at that point is equal to the second highest valuation. So this is exactly like an ascending bid auction. Okay? It's generalizing it to n items, but the case of one item is a special case. Okay? So it shows that bipartite matching market is a more general idea. So you can see this is a very nice idea. It has very good properties. It's also generalization of ascending bid auction. The auction has n buyers and one seller, and the seller keeps increasing prices until one buyer wins. But the matching market has n buyers and n sellers. The sellers keep increasing prices until each buyer has found one seller. So you see, it's generalizing it. Huh? So in fact, auctions and markets are very deeply connected. Okay? So the bipartite matching market is kind of second price auction with n sellers instead of one seller, and all buyers win an item. Huh? In the auction, only one buyer wins, but here we have n sellers, so everybody wins. Okay, that's kind of the difference. In an auction, only one wins, but here they all win. But otherwise, it's very similar. Okay. Okay, so that's very good, huh? So we can see what we saw last week and what we see this week. It's very closely connected. You should think about it and look back to auctions. Okay. Okay, so let me summarize what we saw. So today we introduced markets, okay, where you have interaction between many participants, and the prices are the mechanism. Decentralized coordination. And we introduced an idealized market, and this one has very good properties. Market clearing always happens, okay? Prices can always be found to give market clearing, and each buyer chooses selfishly, and the market clearing prices are also socially optimal. So it's great, in fact. We're connecting the selfish humans with societal benefit. So this kind of a market where nobody cheats is a really good mechanism, okay? Everybody should like it. Capitalists, communists, socialists, everybody, libertarians, I don't know about libertarians, but they're very weird anyway. But most reasonable people would like this mechanism because it's actually good for the individual and for society. And another nice thing is that auctions it's just generalizing auctions. It's a kind of auction. Okay? So all what we saw about auctions is connected to this. So it's all connected, huh? Okay? In a real world, in real world things are not perfectly ideal. Okay? So market clearing is a precise definition of supply equal demand. So in a real world market, it's not so simple. But what happens is that the prices are converging. So the prices will be increasing until there's a buyer, okay? And so the prices are always converging to market clearing situation, okay? So what I show you today is all the intuition keeps holding for real world, okay? Question?
Why do we need such a big financial infrastructure in real life?
Well,
if there is such a simple underlying mechanism.
So this market is something that humans do for a long time. You can go to, people sell and people buy. And if they don't cheat, if they follow the rules, the properties are very good. But in the real world, people will probably cheat, okay? They will collude, so maybe the seller, the different sellers, maybe it's all the same seller behind the scenes. And they start by increasing the conflict, okay? Because they want to increase the prices. That's a cheat, okay? Or maybe there's stealing, maybe there's thieves who steal things, who destroy items, so there's all kinds of ways of cheating. Huh? Maybe there's dumping going on, which is outside of this, where a company is making a product and another one is making a product, and the first one is cheaper. So the second one lowers the price until the first company goes bankrupt, and then the second one is the only one existing. So this is a cheat that's outside of the system. So all the rules and regulations are needed so that people will follow the good system, this nice system. Huh? In fact, that's a good way to see what happens in real life. The laws, for example, if somebody cheats here, it's the role of the government to make regulations so that people follow the rules. So, for example, you can have corruption, where the buyer gives a little bit extra money to somebody, or gives money to some government agent, who then declares one of the sellers illegal, or throws him in jail, or something. So that's all cheating. Huh? So you have to have a framework where people don't cheat, which I'm not talking about. That makes it more complicated. But the good mechanism is no. This is actually a very good mechanism. And real world markets are, if they work well, they kind of approximate this, okay? And if they work badly, it's because there's some kind of cheating going on, okay? Sort of answer your question?
Yeah, it does. But I'm a bit puzzled to why we see such a big inflation.
Why you see? Okay, so there's lots of things. Market is not the whole thing. Huh? There's also things like supply chain, many companies competing for each other. There's things like psychology affecting the prices if there's a war or something, and uncertainty. So, and then there's things like the stock market, which I don't talk about here, which is investing in companies. This is only one small piece of the economy. Yeah? There's many other things. We will talk a little bit of the other ones, but this is not a course on economics, so if you want to know more, you have to take a real course on economics. Huh? But this is important on the internet. Huh? So I'm kind of focusing on things that are internet related. But if you're curious, I'm sure you can find lots of stuff, like a Wikipedia, but this is good foundation. Huh? If you understand this, you already have a good knowledge of what the ideal good situation is. And then how the real world is different is a good question. Huh?
Thank you.
Sort of. So yeah, so it's kind of outside the scope. Good questions, but it's a whole different course. It would be a whole different course, in fact. But see, it's interesting, huh? This economics stuff, huh? And it's related to social network. Huh? Okay. Okay, let me stop here a little bit early, but that's okay. So this is market. So next week we'll talk about more sophisticated situations when you have intermediaries and we have bargaining, negotiation. I think that you would like this. What happens when there's like power plays and bargaining? So we're going to talk about that too. How you negotiate. Okay? Okay, so that's all for today. Thank you.